Hi everyone! In today's lesson, we'll be taking a look at some laws of logs. Just like there are laws of exponents, because logs and exponents are very interrelated, there must exist laws of logs. So, in your notebook, please put down today's subtitle, which is Laws of Logs. There are a number of laws concerning logarithms that will assist in your manipulation of logarithmic expressions. We'll be looking at 4 of the biggest laws. The first law is the following. The first law concerns the logarithm of a product. This law states that if you had a log in base c of a product, suppose I have two variables multiplied together, such as m multiplied by n, this particular property allows you to say that this is equivalent to the log in the same base, c, of the first item in the product plus log in base c of the second item in the product. Let's take a look at a quick example of this law in action. So please put example. And in this example, suppose I tell you that you have the log in base 2 of 2 multiplied by 8. Well, according to this first law, this states that this can be rewritten as the log in base 2 of the first item in the product, the 2, plus log in base 2 of the second item in the product, the 8. Now, let's calculate the value on the left side and the right side of the equal sign, and you will see right away that it produces an equivalency. So on the left side, let's simplify it a little bit. We have log base 2 of 16. And on the right side, we can work out these logs right away. Log base 2 of 2 is equal to 1. Why? Just a little reminder, it's because 2 exponent 1 gives back the 2. And the other expression, log base 2 of 8, is equal to 3. And again, a little reminder, this is true because 2 exponent 3 gives back the 8. Let's continue simplifying the left side of the equal sign. Log base 2 of 16 is equal to 4. Just a little review. This is true because 2 exponent 4 gives back the 16. Equals to, and on the right side we have 1 plus 3, which is 4. As you can see, the first law of logs does in fact work. Let's take a look at another example of this law in action. For our next example, let's try the following. Suppose you have log in base 3 of 9 times 27. We're going to prove that this can be rewritten as log base 3 of 9 plus log base 3 of 27. So, let's prove that this works by calculating the numerical value of both sides of the equal sign. On the left side, when we simplify, we get log base 3 of 243. And finally, log base 3 of 243 is equal to 5. Because 3 exponent 5 gives back the 243. Now, let's take a look at the numerical value of the right side of the equal sign. So, equals log base 3 of 9 is equal to 2, because 3 to the power of 2 gives back the 9, plus log base 3 of 27 is equal to 3, because 3 to the power of 3 gives back the 27, and as you can see, the right side of the equal sign is equal to 5, which is identical to the left side. The second law of log that I would like to take a look at is known as the log of a quotient. This law states that if you were to have the log in a certain base of a quotient, let's say we have variable m divided by n, that will be equivalent to the log in base c of the first item in the quotient, our numerator, m, subtracted by log in base c of the second item in our quotient, the denominator, n. Let's take a look at a couple of examples of this law in action. So, put down an example, please. And suppose I gave you the following. Log base 2 of the quotient 64 over 4. The law states that this is equivalent to writing log in base 2 of the first item in the quotient, the 64, subtracted by log in base 2 of the second item in our quotient, the denominator of 4. Now let's prove that the numerical value of both sides will be the same. Let's start with the left side. When we simplify the left side, it will become log base 2 of 16. And on the right side, we can already calculate the values of the logs. Log in base 2 of 64 is equal to 6, because 2 exponent 6 gives back our 64, subtracted by the second expression, log base 2 of 4, which is equal to 2, because 2 squared gives back the 4. Now let's keep simplifying the left side. Log base 2 of 16 is equal to 4, because 2 exponent 4 gives back the 16, equals to, and you can see right away on the right hand side, 6 subtract 2 gives us 4. Let's take a look at another example of this law in action. Suppose this time I give you the following. The log in base 5 of the quotient 125 over 25. We're going to prove that this can be rewritten as the log in base 5 of 125 subtracted by log in base 5 of the 25. First, let's simplify the left-hand side. Simplifying the left-hand side gives us log in base 5 of 5. And when we simplify it one more time, log base 5 of 5 is equal to 1, because 5 exponent 1 gives back the 5. Now, let's find a numerical value of the right-hand side. Equals log base 5 of 125 is equal to 3, because 5 exponent 3 gives back the 125, subtracted by log base 5 of 25 is equal to 2, because 5 exponent 2 gives back the 25. And as you can see, the right-hand side is equal to 1, which is identical to the left-hand side. Next, let's take a look at the third law of logs. This third law deals with logs of a power. And this, believe it or not, is perhaps one of the most powerful laws of logs. This law states that if you had a log in base c of a power, let's say we have m exponent n, then this is equivalent to if you were to take the exponent n and bring it down to the numerator position, multiplied by log in base c of just the m by itself. This is one of the most powerful laws because it finally allows you to take something that's in the exponent position and bring it down to the numerator position. This will come in very handy later in the chapter, especially in problems that involve determining an unidentified value of an exponent. Let's take a look at a couple of examples to see this law in action. For our first example, suppose I give you the expression log in base 2 of 4 exponent 3. Well, according to this law, it states that this expression is equivalent to writing 3 multiplied by log base 2 of just the 4. The exponent 3 has been brought down to the numerator position. Now let's prove that both sides are equivalent. Let's simplify the left side. Simplifying the left side will give us log base 2 of 64, which will equal to 6, because 2 exponent 6 gives back the 64. Now let's show that the right side will produce 6 as well. The right side will become 3 multiplied by log base 2 of 4 is equal to 2, because 2 squared gives back the 4. And continuing to simplify, you see right away that the right-hand side is equal to 6, which is identical to the left-hand side. Let's take a look at another example of this law in action. Suppose this time I give you the expression log in base 3 of 9 exponent 4. Let's prove that this is equivalent to 4 multiplied by log base 3 of 9 by itself. Let's simplify the left side first. Simplifying the left side will give us log base 3 of 6,561. And log base 3 of 6561 will equal to 8, because 3 exponent 8 gives us back the 6561. Now let's prove that the right side will produce a result of 8 as well. The right side, we will get 4 multiplied by log base 3 of 9 is equal to 2, because 3 squared gives us back the 9, and 4 times 2 does indeed give us 8. Finally, the last law of logs that I would like to look at is perhaps the single most powerful law of all. This law is the one that actually allows you to use your calculators to calculate the log of any base of any number. Because remember, most calculators are programmed by default to use log in base 10. This final law is called the following. It is the change of base law. The change of base law states that if you have the log in any base c of any number m, then to get the result on your calculators, you can simply punch in the default log button, log of m divided by the log of c. Let's take a look at a couple of examples to see this law in action. For our first example, let's pick a combination of numbers that you're very familiar with. Suppose I give you the expression calculate log in base 2 of 64. As you all know, the result will be 6, because 2 exponent 6 gives us back the 64. But if you were to use your calculators, this would be very difficult to punch in, because by default, the log button on most calculators is programmed with base 10 and not with base 2. But using the change of base law, this allows you to use your default log button and simply punch in log of 64 divided by log of 2. Let's prove that when we simplify both sides, it will give us equivalent results. As we know, the left side is equal to 6, because 2 exponent 6 gives us back the 64. Equals to. Now, using your default log button on your calculator, punching in log 64 will give you an approximate answer of around 1.806. Divided by, and again using your default log button, log of 2 will give you an approximate answer of 0.301. And when you do the division, 1.806 divided by 0.301 does give you a result of approximately 6. Let's take a look at another example to see this law in action. Suppose I ask you to calculate the following. What is the result of log in base 5 of 26? So this is basically asking you 5 exponent what gives us back the 26. Now this would be hard to punch in on a regular calculator because the default log button is programmed in base 10 and not base 5. But using the change of base law, you can use your default log button to type in the following. This is equivalent to log of 26 divided by log of 5. Using your default log button, log of 26 gives an approximate answer of 1.415 divided by, and again using your default log button, log of 5 gives a result of 0.699, and when you do the division, 1.415 divided by 0.699 is approximately 2.024. This result is confirmed by the fact that if you were to go back the other way and do 5 exponent 2.024, it does in fact give us back the result of 26. This demonstrates how powerful the change of base law is, because finally you can now use your calculators and the default log button, which is usually log base 10, to calculate the log in any base of any number. And that's it, ladies and gentlemen. This is all there is to the 4 main laws of logs.